Hi Joyce. They're working on these three in the back of their spiral, although I think, was one of them over?
62. And I think we did 60 in class, maybe?
Oh. Anyway, so do your best on them, then come back in just a second and then check them and we'll see how we're doing. Okay, hold on. So the rest of you guys, why is this a lot?
Aha! That's why I went wrong.
Nice.
16 thirds. I don't know how I messed up.
Me neither, man.
What?
Yeah.
4 thirds plus 12 over 3.
Yeah, I got A.
Okay, what did you guys get for 59?
Wait, hold on.
59B.
B.
B.
Long story short, you have y minus b equals e times x minus 1.
Plus.
Number 60. What does dy equal? Hopefully you guys are plugging into secant squared of, and you're doing when pi is equal, well, when x is equal to pi, times 0.5. Secant squared is 1 over cosine squared. Cosine of pi is -1, but squared is a positive 1. So you guys should have gotten d.
First.
Now we're on number 62, and that's the question that everyone has. How? I don't understand.
I got it. It's okay.
How'd you run?
No, I didn't mean like that. I mean, hold on.
Alright, so some of them are trying to do the actual linearization itself. They're saying it was used to approximate. Part of me is like, well, can't we do dy is equal to bring down the 1/3 to the 2/3?
Are you
So
seriously
that'd
doing
be-
differentials?
2/3 dx.
And then the x would be x.
Then we could plug in
Oh,
x
dx would be
is
2, right?
x
dx would be 2?
is
Because you change, dx would be 2, right? Since you're
dx would be 2, and then our x would be at 64.
Wait, if this was like a free response, wouldn't we have to do linearization? We can't use differentials because they'll be like, yo, we asked you for this, you did
Would
that.
be
It's a free response, but it's
66.
not.
I'm just checking to see how it works out. So we could say the dy.
You said B, right?
I got A.
Oh.
Could do dy over y. But to do over y, we'd have to use, oh, it's a calculator problem anyway though.
Why is dx 2?
Because from 64 to 66, so that's the change in.
Oh, okay. So 2 over.
We would
So if it
do 1
change-
over 3 the cubed root of 66 squared.
Oh, well,
Times 2.
yeah, that's gonna be rough. 'Cause
Yeah, see, I don't know if we're gonna be able to do that. I mean, it's a calculator problem. And then we do dy over y.
Wait.
That'll make it like,
And then the cubed root. I think the linearization is the easiest way to go, right?
Yeah.
yeah.
Because then you could just go ahead and do your, well, obviously you still need your y prime.
Even if you did get dy, wouldn't you have to add that to something to say it changed? Because that's just the change in. It's delta. You have to add it to what it to the things. You have to add it to something to find out what it actually is.
Because 64.
Yeah,
And then
you have to add it
the
to
cubed root
4.
of 64 would be 4 equals 1
So it's gonna be
over
like 0.0 something.
3 times, the cubed root of 64 is 4, 4 squared would be 16, right?
Yep.
And it's x minus 60, no.
Yeah.
Second guessing, thank you.
It's not.
And then if you go ahead and do 1 over 48, we're plugging in when x is 66.
Ooh, what?
Yeah, because that's what we're using to approximate, right?
Oh, you just did that a step ahead of me. I distributed first.
So you can say L of 66 is, that'd just be 2 and 2 over 48 would be 1 over 12 and 1 over 12 plus 4, would that be 50 twelfths? Is that right? Plus 4, 48 twelfths.
Wait, not over 12, over
Yeah.
24.
Oh, yeah, you're right.
I don't know what y'all did,
I was trying to go fast.
but
2 over 48 is 1 over 24.
oh.
And 1 over 24 plus 4 would be 96.
Yes.
96 plus 1, 97 24s. Is that right?
These are some fancy numbers
And
here,
that's
Miss Lee.
approximately the cube root of 66.
Which is
Yeah,
for
we're trying to
decimal or
do-
no?
The percent error. It doesn't matter, I would
Whoa,
say keep it precise. So the percent error would equal The change in, which would be 97/24 minus the cubed root of 66 all over, oops, I did that, all over, cubed root of 66.
Misty, you did it
Wait,
differently.
you just did the cube root of 66 minus,
Oh,
No, no.
60, isn't that what we're doing though?
right, I just.
So we're doing the measured minus the actual all over the
I
actual.
think that'd be, oh yeah, that's right. Wow, you're more accurate than mine. I got 4.
It was 4 plus 1/24.
Yeah, but I got y equals 1/48 x plus 8/3. Y equals 64/48 plus 8/3.
2/48, 66 minus 64.
See what else? Oh, I didn't plug it in there. I distributed first, and then I plugged in the 66.
It should be the exact same thing.
That's what I did wrong, actually. I did 64 over
Oh, there you
48.
go, there you go. What do we get as our final answer?
I don't know, because
I got 0.01%.
0.01?
Yes.
I got
Hold on.
Percent, right? So it'd be
0.04 though, so I don't know.
0.000, uh-oh, you guys have different ones.
Yeah.
Plugging in the same thing?
Oh,
I just did, whenever it was on, the homework, they didn't put the cube root 66 on the bottom. They just did the absolute value of one minus the other.
For percent error?
Yeah. Unless I was doing it wrong, but that's how I did it, so that would.
For error, that'd be fine, just absolute value of subtraction, but for
I'm not
percent error, you
plugged in.
have to divide.
Wouldn't you just move it over 2 decimal places?
oh.
0.0001, yeah.
No,
I think you forgot
the
to divide by
subtraction
cube
is
root.
how
Yeah, I
far
didn't,
off,
but they didn't-
measurement wise or amount wise, and then division is per whole. But you're saying in the book, they say percent error is.
Yeah, I could have read it wrong, but I thought that they just did one minus the other.
That's in 5, right?
Yeah.
It's always over accurate, right? Yeah.
Alright guys, grab out a colored pen just to get ready, because we're gonna go and check the evens real fast. Not Newton's, not Smithsonian, not that, what's percent error? 40%, that was a different type. Within 1% of its value. That's different. That's the actual error. Did I give you any percent errors in homework?
Yes. Yes.
I should have, right?
Yeah. But I didn't.
Estimate the percentage error, number 44. Okay, let's peek at 44 when we get there. All right. Let's go and check our evens real fast. We're getting back. So what we're thinking is 0.0, but 0.01, right?
Yeah, I think so.
Percent. But we're going to come back to that as soon as we finish checking. Okay, so Calculus BC, Solutions Manual, Chapter 5, Section 5. What's our first even?
2. Actually.
Oh, that's easy. Where are the exercises? Here they are. Number 2.
I don't like exercise.
Lo siento. Number 2, a is equal to negative 4/5 x plus 9/5. The approximation was 4.92. When they say it differs by, that's just the subtraction in sense of how far off. So 0.0001. Oh, by less than. They didn't even quantify it. Lame sauce. Number next one.
8.
You guys got them okay?
Hold on, 1 second.
Okay. I don't think you need to write that by less than, just subtract the 2. That's the absolute value, that's how far it differs. Number next one, oops, nothing. Beep. Letter A, now they're showing us a lot of things here. They're showing us the approximation. And then they're showing us how it compares, right? You see the actual minus the approximate and how far off. They're just showing us the degree of
Oh, okay, I think
accuracy.
that's what I was looking at.
Okay, that's what I was thinking. So this is just the error.
I did percent error in specific differ.
They weren't asking for that. I mean, you could do that extra as long as you label it, but
Yeah.
they're just asking for error itself, which is just a subtraction. So approximation 1.2, it should be 0.021 off. Approximation 1.003, and it's 9 times 10 to the negative 6 off. That's pretty accurate.
What's the less than 10 again? You said-
This is just them saying like the degree of accuracy, but don't worry, that's not a big deal.
They're 14.
14. Two ways of looking at it. 9 minus 1 over 18, which would be 2 and 7, 162. 161 over 18? You. Or 8.944444.
Is the 80 over 18 plus 9 halves?
No, wait, not 80 over 18. Did I say that? 2 and 7. 161 over 18.
Or 160? I don't know, I think I did the same mistake I did on that last one because I got 9.
But see, Gerardo, why not just subtract and get a negative 1? You know what I mean?
Makes it a lot easier.
Like you're making life hard on yourself. I would just PEMDAS, parentheses, then go to the multiplying.
No, I left it as x at first.
Oh. Yeah, I would not do that. Don't distribute. Life will be easier.
Okay.
Life will be easier. Number next one.
22.
Ooh, I did implicit. Anyone else did implicit?
Yeah, but once you
Yeah.
do implicit, you can't find,
You
you don't have y.
Yeah, you do. Just
You don't
solve for
need-
y in the original.
No, you can't. You can
That's
move it to
why-
one side, and you could
Yeah.
solve for y. You can move it to one side, factor it out, and divide and plug in.
Mm-hmm.
But they didn't. They just left it.
You serious?
Yeah, they left it implicit.
Those freaking little chickens? I did the whole thing.
Okay, this is implicit. They left that as implicit. It's okay. It's okay. Gerardo, I'm proud of you. You got y by itself and plugged in, and that would end up being something gross. Did you simplify the complex
1/16.
fraction?
I got dy is 1/16.
Um, 5 over 100 would be 1 over 20. So you would have 3 over 4 times negative 1 over 20.
So I plugged in at 1.
So it'd be 3 over 80.
Why? I got it all in terms of x and I plugged in 2. And I got 2 times 2 plus 2 squared over 2 plus 2 all over 2 plus 2.
Yeah, without me doing it, bud, I can't follow that. I'm sorry.
Whatever, I don't even care.
But for letter B, weren't you just supposed to plug into, oh, I see, you're plugging into the function itself?
Yeah.
Yeah.
They did something weird. Because I got negative 2x minus y, and I factor out a negative. That might be what I did wrong.
Yeah, because it was a positive 2x all along.
Oh, I see where I went wrong.
So final answer B, remember, this is the time just to write down the right answers real quick and then come back. So negative 0.0375. Number next one.
26. I didn't know this one was the last one. I was so confused.
Oh, just find the differential rule, just like derive that, and then just put a dx at the end.
So but it says d times,
It's not d, it's the derivative, like in a dx. The dx on the other side.
What's the notation? That's on number 26.
I know, I didn't get it either, so I looked at the back of the answers of the ones surrounding it, and I was like, okay.
It's just another way of looking at it in the sense of d of can be derivative of, so you can think dy. So that's your function, 8x plus x to the 8th. So like how we would write d dx, they wrote just d alone. Now usually it's a capital D, but they wrote a little d, and it's just being dumb. But I was just letting you see a new notation. So you're just deriving. Number next one.
The 44. I got here, and my dad came in our room, got mad at me, and told me to go to bed.
Lo siento, 3%. Just get it down, it's okay, we'll come back. 3%.
Yep.
Number next one. Are we done?
62.
62, yeah.
So we did it.
62.
0.01%. So Amanda, I think we're doing good, yeah?
yeah.
Could you explain 41, just part C? It's a, do you think the actual value of f will get, f at x equals 0.1 is greater than or less than the actual? I didn't understand how I was supposed to get
Okay, long story short with linearization, actually let me just get out of this. When we're trying to think of whether or not linearization is an over approximate or an under approximate, do you guys remember how to do this? The AP likes to ask from time to time. How do we figure out?
If it's increasing or decreasing, right?
Not enough.
the derivative is going down.
If the slopes are down, then it's always gonna be,
If the slopes are down?
If the derivative is decreasing.
if the function is decreasing.
Because the answer to the derivative is decreasing, therefore blah 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 blah.
Yeah, but I'm looking for understanding, not just regurgitation. So hold on. How to tell whether a tangent line approximation is above or below the estimate.
That's like Riemann sums, right? if premium sums are gonna be above or below.
It's similar, but different question. Let me show you a few different increasing, decreasing, ready? What if the graph is increasing? What if the graph is increasing? What if the graph is decreasing? What if the graph is decreasing? Question, where would the tangent lines be of this one? Increasing?
Over.
Above. Where would the tangent lines be of this increasing graph? Struggle, see what I mean?
Yeah.
Where would the tangent lines be for this decreasing graph? Above. Where would the tangent lines be for this decreasing graph? Below. It's not based on increasing, decreasing, but what is it based on?
Concavity.
Concave down, the tangent line is gonna be above. Concave down, the tangent line is gonna be above. Concave up, the tangent line is gonna be below. Concave up, the tangent line is gonna be below. So, short answer to your question, Gerardo, when it asks you what you think it would be, is to test the second derivative at that point to see what concavity the graph is displaying at that point. Then you could go ahead and state whether the tangent line approximation is above or below. Now, another way of talking about concavity is saying that slopes are decreasing. Remember, concavity of the original function is the same thing as the increasing, decreasing of the derivative. So we could say that, but we don't necessarily need to go that far, at least as far as the AP is concerned, if that makes sense.
So if concave down, tangent line is above, concave up, tangent line is below. If it's below, then you're gonna under. If it's above, you're gonna over.
Right, because as soon as you get off, you're a little bit below, as soon as you get off, you're a little bit above. Does that make sense? Here we are, related rates. I have a question for you. It's kind of based on, it's kind of based on,
So you want me to do this so much?
it's kind of based on, it's not the exploration in the book. I know, you guys are like, ew, gross. However, what this has you find, I'm not gonna have you guys go super crazy. Basically, it has you graph these parametric functions, and it says the motion of two ends of the ladder can be represented by these parametric equations. The question is, if you have a 10-foot ladder leaning against a vertical wall, the base of the ladder is being pulled away, the top of the ladder is thus sliding down the wall. The question is, right down here, do both ends, or will both ends be moving at the same constant rate?
Oh, that's a good question.
Will the pull away be the same rate as the pull down? And the cool thing is they're actually are able to model this scenario by using parametric equations to split up the y, which is just Pythagorean, and the x, which is based on time, 2 feet per second. And then they said, hey, guess what? You can put this in your calculator. Hold on. You can put this in your calculator and you can graph, given these certain qualifications, and you can see, actually give me 1 second. I have to go to simultaneous mode. One more. There we go. And then I think I have it all ready.
Have you set the window, or did you already set it?
I already said it.
Why is,
They gave me T min, T max, etc.
why is y1 and x2 0?
That's just the
Because you're graphing two different things at the same time. You're graphing the x's, the horizontal motion and the vertical motion
Separately.
separately.
yeah,
So then, look, you tell me, are they moving at the same rate?
No,
Whoa.
No, I don't know.
they're not. The bottom will be going a little faster. I thought.
If you want to, they said you could even change from 5/20 to make it go a little bit faster. You can do like 5/10, which I know would be 1/2, but either way. And then we could graph again.
Looks like it's going faster.
I think it looks the same, yeah.
Okay, it looks the same as far as the points, but you can't look at the points. You have to look at the distances covered.
Mm.
Let's go one more.
Can you zoom square? Because I think the distance on the bottom is a little.
Yeah, I can do that.
Can you just make the x, or yeah, the x max the same as the x min? No, you can't. Or the x max the same as the
I wonder how much it'll mess it up if I do zoom square. I'll try.
Yeah, the bottom one covers a greater distance.
The bottom one covers a greater distance. Now, if you want to be super snazzy, the book actually tells you how to write a program, which I did last night. And if you hit program, and if you hit ladder, and if you hit run, it doesn't do anything until, and then you see the ladder falling. What?
That's
Go
so
team.
See what I see?
You can see it if you want. Just do second quit.
That is witchery.
And then run the program, go up and then run it again. It's pretty nifty. But anyway, long story short, the question is, are they going at the same rate?
No.
Does he have to press enter again?
Yeah, press enter after you.
One more.
Does it make a difference of how tall the ladder is?
It'll make a difference in the sense of what the rates are, but it's not gonna make a difference in the sense that they're not gonna be the exact same.
How long did it take you to write the program?
Steve, that is so lit.
I didn't write it off the top of my head, it literally was underneath this example, I was like, sweet, and it was pretty cool.
No, but I did like to copy it in.
So you
Oh,
quit
it's a
and
short
then
program,
press.
it's not that big. You can look at the edit, just don't mess it up yet. So anyway, long story short, just because the vertical and the horizontal is both a part of the same ladder doesn't necessarily mean they move in the same way, which gets us to this whole idea of related rates. Starting with a cone that's leaking. We're not solving an entire problem, all we're doing is
Oil leak?
That is so cool.
I don't know if you did something, I don't know how to do it again.
You did magic. It's math magic.
Oh no, not this again.
again.
In physics, there was this thing where like the spout, it was coming out fast at the bottom of this huge tank, and at the top it was like basically not moving because it was a Bernoulli's principle one, and I just wanted. Oh.
I just have to remember what I got on it,
So
to
maybe
see if I got the right answer.
Oh, the cone.
See,
thing?
I used to do them right after, and I had to have fun with it, but then, I don't know.
I just don't
Some
remember
people
how to
do.
do any of it, so.
Could you go back?
Okay. Oh, you don't have to write down the ladder.
Map one more.
Take a picture.
Restricted.
I got it, Gerardo.
It's online.
Oh, yeah.
It's online. Okay, never mind. I'm just gonna
So
skip
then
line.
coming back.
Skip line.
Long story short,
Me
so
too.
just because two different dimensions or two different measurements of one singular object, just because they're of one singular object does not mean that they change in the same way, or I should say at the same rate. So therefore, an illustration of this fact is, what if we have water in a cone? And what if the water is draining from the cone, from the bottom of the cone? In order to figure out how their rates are related, we have to think about how the quantities are related first. So, the way that we start with figuring out how their rates are related, which they are related, but they're not necessarily the same, and I have to add in that necessarily the same. We start with what's the relationship between the quantities, and if we're talking about water in a cone, we have the quantities volume and radius and height, right? Well then, how do we get to rates?
Either
With the
derive or
secondary.
We derive.
Don't we need a secondary equation?
Yeah, we can get a secondary equation.
So we can plug in for R, or plug in for everything.
If we're trying to solve, we're just trying to look at the idea.
Oh, okay.
So then, if we're trying to figure out the rates, we need to take the derivative, but the derivative with respect to what? We want to know how volume is changing with respect to radius? No. Volume with respect to height? Rarely. We want to know how all of them are changing with respect to
Time.
So therefore, if we know, long story short, if we know the relationship of the quantities, then we can find with quick implicit differentiation, not forgetting our chain rule, like the derivative of v is 1 dv dt, et cetera, with the product rule, we can see the relationship between all of these rates as far as how dv relates to dh and dr, and similarly radius and height itself. Now, the dilemma though is, in a lot of problems that you're going to see, this is the relationship of the rates, right? In a lot of the actual problems where you're solving for numbers, et cetera, they're gonna give you one rate, and they're gonna ask for another, but what's the struggle in this problem? If they gave you one rate, and they asked for another,
You need 3 rates
I need
altogether.
3 rates altogether, so either, here's where it comes in what George was saying, so either we somehow, before deriving, get h in terms of r or r in terms of h in order to not have this extra rate, or we have a secondary equation that we derive to figure out how these two, for instance, rates are related, so that if we have one, we can figure out the other, so we can plug in to find the third. So it's all a question of what do you have, and what do you want to find, or as the book says, what are you seeking, and what are you given? And then you have to use your previous foundations in math in order to be able to take the clues and figure out that it truly is enough to solve. Now, don't write this down. I thought it was, I added that, the textbook actually has a helpful information. I thought it was kind of interesting in a sense that it's kind of talking about how important related rates are, in that the big distinguishing characteristic between calculus and algebra is calculus's ability to deal with variables that change over time. And so with this whole idea of related rates, it's literally talking about how one quantity is changing in relationship to 1 or 2 or 3 or however many other quantities are in the actual formula. And then it's talking about how it's one of the most important applications of calculus. Anyway, I thought it was kind of cool. So, they have, oh man, 6 different steps to solving related rates. I have my quick little sum up on the next page, hence why you probably shouldn't write this one. However, it is interesting where they say you should start.
Understand the problem?
Yeah, read it and figure out what's going on. And figure out, wait, do you see it? What you are seeking and what you know. Yeah?
Given.
What you are seeking, what you are knowing. Then you need to figure out a mathematical model, whether it's pulling out a formula from geometry about like figures and volumes and surface areas, or whether it has something to do with actual parts of a graph, like a Pythagorean or a distance formula, etc. You need to think about which, as this situation, it's a story, as this situation is playing out, what's changing and what's not. Is there anything like the ladder problem where as the ladder falls, hopefully it's not changing height, it's the same ladder, right? Unless it breaks in two, that's a whole other thing, but, right?
Changing height.
If the ladder is,
Changing height now. Like the
well,
hypotenuse.
sorry, height, you're right, length of the ladder. I was thinking height as in here's the ladder's height.
Oh,
But the ladder will have a constant height and length, so then we won't need to worry about him varying or changing, because he's not gonna vary or change. What things are constant, what things are variable, and then working with those in the sense of when we come down and we relate the rates, aka we relate the quantities first, we take the derivative, thus seeing the relationship of the rates. If something is constant and not changing, its rate is 0. Double check that, make sure you're okay, etc., etc., etc. And then interpret what you have. My way of saying it goes something like, what's the given, what's the find? In their terms, what do you know and what do you seek? We both say draw a picture, labeling as much as possible. Labeling as much as possible. Now I say labeling variables, but technically, label variables with variables anything that is changing as the scenario plays out. However, can you label constant values or values that remain constant? Yes.
Look with the ladder.
Now, does that mean plug in all your constants? No. The constant refers to a number, true, but in this scenario, a constant, or when I say values that remain constant, you have to understand the difference between them giving you a number at one instant of the scenario, and then them giving you a number that stands for this measurement the entire time of the situation. Does it remain constant or does it change? If it changes, you better make it a variable because it's varying, right? If it remains constant, plug that puppy in because I don't need a variable for him. So hence, when we write an equation relating all of our different quantities, whatever all is being measured, etc., in a problem, plug in any constant values, and by that I mean values that remain constant, right? That are not varying as the situation plays out. Use chain rule and implicit to take DDT of everything. Plug in what you know. Plug in what you know. But sometimes you have to plug in or keep thinking deeper, right? Because sometimes just plugging in what they give you, and if you were a monkey and you were just like, ooh, number, pull out, ooh, number, pull out, and you just plug in, sometimes that's not enough. Sometimes you have to think, wait a minute, based on my previous training in math, what else can I know? What else can I know? The most common example being radius and height, sadly, of a cone. Because they love to say something like, hey, you know this and you know this, and I won't tell you much else because we're supposed to think similar triangles and then think about ratios. It's rough. We'll get there. Those are my steps. Those are my clues. So let's start with an easy one.
When you say clues, do you mean interpreters?
Suppose x and y are differentiable functions of t and related by, oh, look at that, they're giving me the relationship of the quantities.
Oh, schmucks.
Easy cheesy, look at this. Then what are they asking me to do? Find the rate of y. Can't get any rates until I do what? Yep, I need to derive. We have the relationship of the quantities, which allows us to get the relationship of their rates. So dy dt is equal to 2x dx dt. And so all I have to do, nice thing is they gave me everything I needed. They gave me the relationship of the quantities. They stated what I know and what I wanted to find, so we just went for it.
We get 1x equals 1, 1x equals 1.
Uh-huh. When x equals 1, we also know that dx dt is equal to 2. And long story short,
Equals 4.
oh my goodness, this is a struggle.
Oh my goodness.
There we go.
Oh, my.
dy dt is equal to 4. And we have no idea units, so we leave it and say whatever, that's the rate of change. 4 changes in y with regard to 1 change in t.
Where'd you get dx dt?
Ah, the struggle with implicit. Remember? When we're taking the derivatives of y's before, it was ddx, and so there was a outstanding y prime. But now that we're taking the derivative with respect to t, both x and y will have their own respective u primes or their own respective chain rules in the sense that the derivative of y is 1, but I need dy dt because y has a derivative with respect to t. Same thing here, since t and x do not match, since I'm taking a derivative with respect to another variable, x is changing based on, and he has a rate of change as well. Time is my independent, no longer x. Does that make sense, Strata? Okay. He wasn't too bad, yeah?
3, 2, 1, 2, 4.
So we're just taking our clues. So they said, find it when x is 1. Oh, and by the way, when x is 1, dx dt is 2. Oh, plug in, done. Is that okay?
For sure.
So what if we have something a little more interesting? Ooh, a rising balloon.
A balloon.
A balloon is rising straight up from a level field. Look, he has a little basket, he has a little bit, and then
Oh, you got a little basket.
there's a little person inside. There's a fun design. Da, 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 da. Okay, so we have a balloon. It's a little distorted. We have a balloon, hopefully not in that basket, rising up from a field. It's being tracked by a rangefinder 500 feet from the liftoff point. We assume when it says straight up, it's at a 90-degree angle, yeah? And we assume when it says 500 feet, it's talking about horizontal distance, so we can make it perfectly flat. At the moment, the rangefinder's elevation angle, angle of elevation to the who?
To the
To
balloon.
the balloon. So we have a theta.
That equals.
Now, why am I not plugging in pi over 4? Yet.
Because it depends on where it is.
The balloon is rising, the angle is always changing, the angle is varying. They gave me an angle, but that is not a constant. Is there anything else I can label?
You can label the rate, is the angle's increasing at point? No, we can't.
Just the picture though.
Yeah, just a picture.
I mean, I could make this like an x or a y. Do I have to make this one a y or another
Can we
variable?
make
500,
Why is it 500?
Because it
because
says.
it always will be. It's
The
a
radar
constant.
is fixed. The rangefinder, I should say, is fixed.
Can we make the x or y because we're equal?
You have 500 equation. Okay. Good. So what do we know? Well, we know the 500, we already plugged him in, so let's not go too crazy. I labeled this
We
given.
want to find y, so opposite over adjacent.
What we're seeking is our find. At the moment, the rangefinder's angle, the angle is increasing, We're trying to find how fast is the balloon rising? Whose rate would that be? What's rate would that be?
dt.
This one. I want to figure out how fast y is changing, or the height of the balloon is changing. So find dy dt. They give me a such that, they give me an instant, a snapshot in time, and that snapshot in time would be theta equals pi over 4, technically radians. Snazzy thing though, radians are dimensionless. We'll get to that in a second.
Oh.
What are we given?
Okay,
The angle is increasing at the rate of, so we know d theta dt. They still give us radians per minute, just so we can go ahead and realize it's d theta dt, but once again, radians are dimensionless. They adapt to whatever unit is being used, which is nice. How fast is the balloon rising at that moment? Oh, dy dt.
And then you plug it into a calculator.
Oh, we can't plug in anything though, because we haven't related the quantities
Oh,
yet.
Tangent.
Tangent.
I'm a little ahead.
We have to relate the quantities, we have to get a formula first. Because if we don't have a formula, then we can't relate the rates and we can't do anything with the problem. So we are gonna start with tangent of theta is equal to, why are we using tangent? Because we know nothing about the hypotenuse, that's silly. But we do know something about the opposite and the adjacent, so I can make it y over 500. Another way of seeing it is 1 over 500 y, right? So if I'm taking d dt, I can have secant squared of theta, d theta dt, equals 1 over 500
Wild.
dy dt.
What did I do?
Remember,
I multiplied the 500. Forgot to
and now I'm going to plug and chug and solve.
Yay,
Now, I do have an AP last year, example that I want to look at on Monday. Our test is going to be Tuesday or Wednesday. I'm totally fine having it Wednesday if we need another day on related rates. So guys, do the best you can on homework over the weekend. I didn't fill in the blanks up there because I was still kind of feeling it out. We're not going to spend all day Monday on related rates, but we will spend most of it. So work on homework some, but I know this weekend's homecoming, the juniors are all gone, it's okay if we take a day and we have our test on Wednesday. So let's establish test on Wednesday, review day Tuesday. Monday is finish the notes / work day. If you want to do a little bit of homework, that's good. Sound good? Already said good. Bye guys.
Bye.